Hey, welcome to this video. Today we're going to talk about chirality, kind of give a brief introduction into isomers, stereoisomers, optical isomers, and then in the next video we're going to go more in depth on how to apply chirality, and then talk about the Kohn-Ingold pre-log rules and how this affects optical activity. So, like I said, today we're just going to proceed with the basic understanding of what makes something chiral and what is chirality. So I like to start off with this little flow chart here, and I think this is a great representation of the whole course, really, what we're going to talk about in organic chemistry. But today we're really mainly focusing on this section here of optical isomers and then enantiomers, which is it seems like a very small part of the flow chart, but it's a very big concept in organic chemistry. So we're going to follow down to what are isomers, and we kind of already know what isomers are. They're the same compound, the same molecular formula, but different structural connectivity. And so this kind of goes into, okay, well, if it had the same connectivity, then it's a stereoisomer because and then we follow that down to, is it configurational, and if it is, and if it's optical, and we'll really kind of go into the rest of these later on in the course, but today, like I said, we're going to just mainly focus on enantiomers, okay? So again, isomers are the same compound, with the compounds the same chemical makeup but different structural connectivity. So basically what that means is they're different structures, okay, and the structures are different. And so stereoisomers is, okay, well, let's say you're connected to the same atom, but now you can have different spatial arrangements, and this is why it's a very important thing to have in organic chemistry is a molecule kit, because now we can attach it spatially different and you can have a completely different molecules, and that's what makes something chiral or achiral. And so now, so what that basically means is same atom connectivity but different spatial arrangements. So those are a subclass of isomers, which is called a stereoisomer. So now we're going to kind of get into chirality. So what it means to be chiral, essentially what it means in organic chemistry is it's just a carbon within a large carbon compound, or it can just be a single carbon, and it just has to have 4 different groups attached to it. And so these 4 different groups can represent something of a larger carbon chain like this, or it can just be a fluorine, and this one could be a bromine, and this one could just be a hydrogen. And so this could be 4 different groups, or you can have 2 different carbon groups, right? 2 different carbon groups that are different than the one on this side, and it's also different than the one on top. You can have 4 different carbon groups, and that's going to make it achiral, or a chiral, right? As long as there are 4 different groups attached to a carbon, the compound will always be chiral. So that's a shorthand to remember. Okay, so essentially to determine chirality is if they were to have 4 different groups onto it, then you can essentially make a mirror image of a molecule. And so that's what chirality means, because if two molecules, if 2 molecules are mirror images of each other, or they can make mirror images of each other that are non-superimposable, then it's a chiral compound, okay? And you can have compounds with multiple groups of 4 different carbon groups, but some can not be chiral. Okay, and we'll get into that again in the next video when we talk about meso compounds. But in this case, we're talking about what makes something chiral or achiral. Again, if 2 molecules are mirror images of each other, non-superimposable, they are chiral. And if they are superimposable, meaning that you can just like shifting them around in space, rotate the actual whole carbon compound itself, and it can be the same, then they're achiral. So again, what we talked about last time, right, about 4 different groups attached to a center carbon. In this case, we have an example of a single carbon attached to a fluorine, a chlorine, a hydrogen, and a bromine. This compound is chiral because it's attached to 4 different groups. And then the compound on the right is achiral because it's only attached to 3 different groups, a hydrogen, a chlorine, and a fluorine. And chirality, to determine its chirality, we have to know that it has a mirror image of each other. So this is a 2D representation of another carbon compound. In this case, this ET represents ethyl. The CH3 is a methyl group, so this has a methyl, ethyl, and then a chlorine in the hydrogen. Imagine this blue center line represents a mirror, and this reflection is shown on the right. And we can see that this is a mirror image representation of the molecule on the left. And so this is a 2D representation of a chiral compound. Okay. So a 3D representation, and in this case, if a molecule can do this, if a molecule has a mirror image of each other like this, and it can do that, then it's a special pair, and that pair of molecule is called enantiomers. So enantiomers. So again, if a compound's chiral, then it always have a pair of enantiomers. And enantiomers is just the name to say of the two compounds that are mirror images of each other. And really, we see this in every day in our lives, because if you look at your left and right hands, those are a pair of enantiomers. Great example, because they are mirror images of each other, but if you try to superimpose them and move them around, if you put your left and right hand on top of each other, they can never be exactly the same, right? So this is now a 3D representation of enantiomers. Now I'm using that vocabulary because it's very important that we understand that, because it's going to be thrown around a lot. So in this case, let's represent, this is using a wedge and dash representation of the molecule with a fluorine, a chlorine, and bromine, and a hydrogen, as we saw previously. And if we were to put a mirror right here, and then this is the mirror image reflection on the right, okay, and you could say that these are mirror image reflections, right? Right, because this hydrogen is pointing, it's facing each other, right? And then the chlorine is in the back, and the chlorine's in the back on the left one. And let's label this compound A and B. Okay, so how do we check that these two compounds are enantiomers? How do we know? Okay, well, if we're to take compound A, and we're going to check its chirality. If we take compound A, so this compound A, this is just a repeat of the image above. If we take compound A and we rotate it 180 degrees here, okay, and we rotate it 180 degrees, what we get is we go from up here, this compound, to here, right? We rotate it 180 degrees now. You see that? This hydrogen is on the left side, now the hydrogen is on the right side. And now if we compare this to compound B, we bring down compound B, they are not the same. Okay, because this chlorine is coming out of the plane, but in compound A, the chlorine is in the back of the plane. Okay, and so no matter how hard you try to rotate compound A, it'll never be exactly the same as compound B. And this would make this chiral and also enantiomers, because it's compound A and B are mirror images of each other. Okay, so indeed, they are chiral and enantiomers. But again, why is this important? Because it seems almost too simple, and it kind of seems like it doesn't, well, they're kind of the same thing. Like, why does it make any difference? So I'm going to show you a real world example that's quite interesting. So if we look at this compound down here, I represented the blue circle. This represents the chiral compound that's within this larger carbon chain. We call this a chiral center because it's very rare in organic chemistry that we'll see a compound like this, right? We don't see compounds with a single carbon attached to, 4 different groups that are single atoms. Like, I mean, you might see it, but it's less common than something that's part of a larger compound, right? Because a lot of pharmaceutical drugs are big compounds. And so in this case, we have a representation, a visual representation, the structure. So the left carbon, or if the left compounds, this is called L-methamphetamine. The right compound is called D-methamphetamine. And if you look at the chiral centers, if you were to rotate the left compound 180 degrees, if you focus on this dashed methyl group, essentially what this represents is a CH3 group, and it's just dashed. Okay, and that just means it's in the back of the plane. If you were to rotate this whole compound, though, 180 degrees, and you overlap it with the compound on the right, the D-methamphetamine, would it be exactly the same? And your answer is no, because this will shift out of the plane, and it will be a dashed. It will be a wedged compound, not dashed, which would make it an enantiomer. Because now, if you think about a mirror here, these are mirror images of each other. D and L-methamphetamine are mirror images of each other. But why is this important? Well, L-methamphetamine is a nasal decongestant. It is commonly sold as Vicks vapor inhaler, and you can find this in any drugstore in America. And it's L-methamphetamine. However, its mirror image counterpart, D-methamphetamine, is actually a psychoactive drug, and it's illegal. It is a class 1, a schedule 1 illegal psychoactive drug, right? It's meth. And so this is why it's important, because something that simple, something that's just one shift of that methyl group would make it an illegal compound that's highly addictive and highly destructive biologically. So that's why it's important to understand this, and it plays a huge role in organic chemistry. So how do we find these so-called, or identify these so-called chiral centers, quote unquote chiral centers, right? And so essentially, we're just looking for molecules, or if we're looking at a big molecule, we're just looking at a carbon that has four different groups. And in organic chemistry, we call this a WXYZ group. And these WXYZ groups essentially represent four different groups. And like mentioned before, they can represent something of a larger carbon chain. So this Y can be like a 4-carbon chain, and this one could be a 3-carbon chain, and this one could be a single methyl group, and this could be a hydrogen. And this would make it a chiral center, right? Because now it's part of a larger carbon molecule, but it has four different groups attached to it. And the best example here, the most simple example of that is here, right? This is a butane or butanol group, so it's a 4-carbon compound that's an alcohol because you have a OH group. This indeed only has one chiral center. It has the chiral center that I've kind of blown up and over exaggerated, but you see that this has an ethyl group, a methyl group, and an alcohol group and hydrogen, and that's going to make it four different groups, and that's going to be chiral. And mathematically, it's said that if you were to have 2 to the nth power, n representing the number of chiral centers of a compound, that is the maximum number of stereoisomers you can have. And statistically, if you think about it, right, each chiral center can have a variation of stereoisomerism. You can spatially rearrange it differently a certain number of times, and you can do that to every single center, right? And then you can statistically have a probability of getting all the numbers of stereoisomers. And so some mathematician figured out that 2 to the nth power, n representing the number of chiral centers, gives us the maximum number of stereoisomers possible. So a very good shorthand to remember. Okay, so now we're going to kind of go into how do we identify chiral centers, okay? So I kind of already did a brief example, but let me get rid of all this. But really what this means is a lot of writing. Sorry about this. Okay. So if you look at this, if you look at all the blue circles, these blue circles represent the chiral centers. And this is norethindrol, and this is an oral contraceptive. So very common compound that you're going to see in organic chemistry, these big ring structures, right? So let's focus on something that's achiral. If we look at this compound here, this carbon here, if we blow this up, this really represents as it's attached to two different groups, this going to left and right, and it has essentially just two hydrogens coming out this way. And that's not represented in this ring structure, but that's what it makes. Basically when you see this, that's what it basically means. This is what it looks like. And automatically we can just cross out that this has no possibility of being a chiral center because it has, it doesn't have four different groups. It has two hydrogens. Automatically that says no, cannot be a chiral center. So that means that I'm going to represent it in red. So this means that this one, and even this one, because this only has three different groups, because this double bond stops that carbon from having the fourth group. So this only has three different groups, which would make it achiral again. And even so, this one too, and this carbon here, this carbon here, and this carbon here, and this carbon here, and here, here. So now all we're left with is, okay, well, how about the carbons as represented in blue? And so the best way to figure this out in a ring structure is what we call tracing. So I'm going to represent this carbon. I'm going to blow this one up. So if we were to blow up this to scale, what it really looks like is this carbon here. It has this group, and it's part of this pentane, cyclopentane group. And you have this alcohol group, and then you have this carbon triple bond group. Okay? And this is part of a, again, larger carbon chain, I guess, on the left side, right? So if you were to trace this carbon, and I'm going to represent in green, if you were to trace it this way to the left, what happens is you first run into this carbon here, right? And this carbon is part of a much larger group here, and this is completely different than if you trace it from the right side, right? If you trace it from the right side, this second carbon does not look like or this first carbon that you run into on the right side does not look like the first carbon you run into on the left side, meaning that this carbon is attached to two different groups already, part of this ring structure. So 1, 2, and then you have this alcohol group, which is the third different group, and then you also have this triple bonded carbon group that you don't see anywhere else. So this means that this has 4 different groups attached to this carbon, which would make it a chiral center. And if you were to use this methodology and you look at everything else that you see here, we come to find out that this has 5 different chiral centers. 1, 2, 3, 4, 5. And so 2 to the 5th power is 32. And this is the maximum number of stereoisomers you'll see in norethindrol. Okay, so kind of a brief summary of what we just did. Ring carbons with chiral centers. You basically trace the carbon, and so from 2 different directions. So again, an example of this is if you look at this carbon here, and we're to trace it going down, and we trace it going to the right. What we come to find out is you run to this oxygen group in the first adjacent compound next to it, and then if you go on the right side, you just run into a carbon, meaning that this is automatically attached to 2 different groups. However, you have these 2 hydrogens, and so this would make it achiral. Okay, but a better example, I think, is this one here. And if you just focus on essentially the chiral center here, or that blue circle, if you focus on that, and if you trace it going to the right, the first carbon that you trace is in part of this double bonded structure. However, if you were to trace it going to the left, this first carbon is just attached to another single carbon, a single bond, and so this would make it a chiral compound, because now you have 2 different groups going in 2 different directions, traced in 2 different directions. Then you have this alcohol group and also this hydrogen, and so this would make it a chiral compound because you have 1 chiral center. And so if you have 1 chiral center, then it's going to be a chiral compound. However, we'll kind of get into special cases in the next video where if you might have 2 chiral centers, but it could be achiral. The whole compound itself could be achiral. And so another way, if you were to look at the same compound, but you shift this double bond onto this carbon, or in this part of the chain, now if you look at it, you have some symmetry. And again, this blue line kind of represents this line of symmetry, because look, if you look at it, if you exclude these 2 groups down here, right, pretend they don't exist right now, well, we see that you see the symmetry going this way and this way, right? If you were just following tracing out, again, just tracing out the carbons from either side. This would make it achiral because now you have this line of symmetry. So if you were to go this way, it's completely identical if you were to trace it from the right side. So achiral, because now these 2 groups are completely identical. And so this kind of goes into this idea of the plane of symmetry. Molecules with a plane of symmetry, or even a line of symmetry, would make it achiral. And so molecules, but chiral centers too. So again, or not chiral centers, but carbon centers, really you can determine if it's achiral or chiral center. So again, if you look at the simple representation of this carbon attached to hydrogen, fluorine, 2 fluorines and a chlorine, you have this plane of symmetry between the 2 fluorines, which would make it achiral. And we know that because in order to have a carbon that's achiral, if we're looking at something that's only attached to 4 different atoms, then you need to have 4 different groups or 4 different atoms. So another representation of this cyclobutane group here, if you look at it, these 2 oxygen groups or these 2 alcohol groups are just diagonal to each other, and if you trace out these lines here, these blue lines, these dashed lines represent this line of symmetry, which would make these carbons achiral, so they wouldn't have a chiral center. They wouldn't be chiral center. In this case, this compound therefore has no chiral center, so this is achiral. This whole compound is achiral. So now that kind of goes into this idea of why is it important to have, why is chirality important? And then what does it have to do physically, and how does it help organic chemists? So a little history lesson. In the 1800s, we had a French physicist, Baptiste, and he essentially said that if you had he was discovering light, right? Not discovering light, but he was just playing around with light, and he come to figure out that, hey, if we put a polarizing lens, hopefully you guys know what that is, but I'll kind of describe what that means. But if you had a polarizing lens and you put this beam of light through it, then you have this plain polarized light. And basically says you can't polarize light unless light is also acting as matter. And so you have this whole idea of wave particle duality, right? Because now it's like, okay, well, we thought that light was a wave, but if light is a particle as well, then you can polarize it, and that's what happened. You can polarize light. And so if you were to represent what light polarization is, and imagine that light is just a bunch of random vector fields, and you were to put this through a polarizing lens here, right? A very bad representation. But what happens is, there's different types of polarizing lens, but what is to come out when you polarize the light is now you only have these vectors going in a single direction. They're all aligned. And this is called plane polarized light because they're all within the same plane. Okay? And so this is very important because it is discovered that now if you put a chiral compound in front of it, so you can have this like little cuvette, and we call this whole machine called a polometer. And so you put this like tube of a chiral compound in here. What is to come to find out is if you were to shine this plane polarized light, what happens is this plane polarized light is rotated a certain degrees, and all these vectors come out. Again, they're still polarized, but now it's rotated a certain number of degrees, and that is what they discovered. And they discovered that if you put a chiral compound, it shifts plane polarized light, or rotates plane polarized light, and this kind of goes in this whole idea of optical activity. And so you fast forward like, a couple number of decades, and what happens is you have this guy named Louis Pasteur, and he's studying tartaric acid in winemaking. And he figured, well, okay, grapes have tartaric acid. We can lab synthesize tartaric acid. And so he came to find out that grapes producing their own natural tartaric acid is different than the one that was synthesized in labs. And this is the visual structure of what it looks like. But again, if you have these chiral centers here, then you can have different spatial arrangements. And we're going to have to represent that in the structure. Which one are we talking about? So the one in grapes, if you were to put this molecule side by side, it is said that these these alcohol groups are wedged, as opposed to the synthetic one where they're dashed. And so that means this oxygen group is these alcohol groups are arranged spatially different than the one found in grapes. And so this is very important because we can tell that these two compounds are chiral, and these two compounds represent an enantiomer. If you were to rotate this 180 degrees, it wouldn't be the same. But they are mirror images of each other. And that's why it's very important to understand this. Because now that we know that these are enantiomers, how does mixing them affect the rotation of light? Because we know that chiral compounds can rotate light. Come to find out, when Louis Pasteur synthesized tartaric acid, and you'll really figure out why this happens. But what resulted was he essentially got a 1-to-1 ratio of this synthetic structure and the naturally occurring structure. He when he synthesized it, he got both structures in equal amounts, and that's called a 1-to-1 racemic mixture. And what happened is it had no rotation. It was optically inactive. And so racemic mixtures, 1-to-1 equal mixtures of the same enantiomer or of enantiomers, result in no rotation, so optical inactivity. And so, but we know that chiral compounds have optical activity. So the only way you can have no rotation of light is either you have a racemic mixture of the two enantiomers, or you have a achiral compound. Achiral compounds, right, have no optical activity. And so this is very important because if you were to synthesize a compound and we wanted to know the type of enantiomer or the type of stereoisomer we had, we could tell if it's going to be a chiral compound or not by rotating light. And if we have a collection of data, we can just put this through a sample of it through a polarizing light and know the exact number of degrees that the light was rotated counterclockwise or clockwise, and that could help us determine the exact type of isomer that we have. And this is the whole idea of optical activity. So that ends the video here. Is kind of giving you an introduction into chirality, and again in the next video we'll talk about something that's more in-depth about enantiomeric mixtures and excess and specific rotation. But for now, this was just an introduction into chirality. So I hope you found this video helpful. If you did, please give it a thumbs up, like it, share it, and don't forget to visit my website.